This solid titanium aerospace component features a highly engineered surface that is polished to an absolute mirror-like reflectivity. This dark polymeric surface is highly textured, causing water droplets to bead and roll off the material instantly. These two finishes share a common origin, a specific method of atomic engineering. That process is physical vapor deposition, or PVD. PVD involves stripping a solid source material into a gaseous vapor and reconstructing it atom by atom onto a new surface, called the substrate. By controlling the specific environment where these atoms land and link together, engineers define a material's visual identity and mechanical durability. High-end surface aesthetics are the intentional, macroscopic manifestation of controlled nanoscale physics. PVD requires a high vacuum chamber. This diagram shows air molecules being rapidly evacuated from a sealed environment to ensure the space is completely empty before the process begins. The vacuum minimizes chemical contamination and removes physical obstacles that would interfere with the coating growth. Vaporized atoms must travel in a straight line to the target. Without the vacuum, collisions with rogue gas molecules would scatter the vapor and ruin the final structure. Inside this vacuum, extreme localized energy is directed at the solid source material to break its atomic binding forces. This energy is delivered through mechanisms like thermal evaporation, high-power electron beams, or ion bombardment. This input forces the source material to atomize or ionize, ejecting it into the vacuum as a vapor phase. The combination of a total vacuum and extreme energy enables the precise, collision-free transport of matter across the chamber. When vaporized species reach the substrate, they stick and begin vibrating. This initiates nucleation through adsorption. These atoms then undergo surface diffusion, sliding across the substrate to find an optimal resting place before locking into position. The final position of these atoms is determined by the thermodynamic-kinetic balance. Thermodynamics drives the system to minimize surface energy, which encourages atoms to clump together. Kinetics acts as a barrier to that clumping. Variables like deposition rate, substrate temperature, and atomic mobility can prevent atoms from reaching their lowest energy state. Increasing the substrate temperature provides atoms with more kinetic energy, allowing them more time to diffuse and find ideal structural alignments. Conversely, a high deposition rate can overwhelm the surface, burying atoms and freezing them in place before they can find an optimal position. These frozen defects and residual stresses dictate the long-term integrity and lifetime of the coating. The final density of the coating is a snapshot of this thermodynamic and kinetic battle. The interaction between the substrate and the vapor forces atoms into one of three distinct growth modes. The first mode is island growth, or Vollmer-Weber growth. In island growth, vapor atoms bond more strongly to each other than to the substrate, causing them to aggregate into isolated vertical stacks. This mode creates highly textured, porous, or matte aesthetics due to the mountainous topography of the atoms. The second mode is layer-by-layer growth, also known as Frank van der Merwe growth. Here, atoms bond strongly to the substrate, completing entirely flat, two-dimensional sheets before a second layer begins to form. This yields smooth topography, resulting in highly reflective, mirror-like finishes. The third mode is layer plus island, or Stransky-Kristanov growth. This hybrid mode begins with flat layers, but transitions into island clumps as lattice mismatch strain builds up. Lattice mismatch refers to the difference in atomic spacing between the deposited film and the substrate material. Managing that lattice mismatch is essential to controlling which structural path the material follows. Engineers manipulate vacuum pressure and energy input to trigger the specific growth mode required for the final product. Whether a surface acts as a mirror or a textured absorber is decided by whether its atoms form as islands or layers. Beyond aesthetics, the material and the interface geometry determine the mechanical adhesion and functional durability of the coating. PVD adhesion relies on chemical bonding at the interface and physical-mechanical interlocking. Engineers will often use abrasive sandblasting before the deposition process begins to increase the surface roughness of the base substrate. This artificially induced roughness provides microscopic crevices and valleys. As the vaporized atoms rain down, they fill these jagged features, creating an interlocking joint that reinforces the mechanical adhesion strength. Ceramic materials are also chosen for specific functions. For instance, yttria stabilized zirconia, or YSC, is a ceramic used for thermal barrier coatings. YSC is a zirconium oxide-based ceramic, stabilized by the addition of yttria, allowing it to maintain structural integrity at high temperatures. Complex alloys or nanoparticle functionalized polymers can be deposited to alter the surface texture, engineering properties like hydrophobicity or wear resistance. Surface preparation and material choice bridge the gap between a fragile atomic layer and a robust functional component. This process explains the titanium and polymer surfaces shown at the beginning of this film. The reflective perfection of the titanium was established when its atoms were forced into a layer-by-layer growth mode. The hydrophobic texture of the polymer was defined by the thermodynamic forces dictating island-based nucleation. PVD utilizes total vacuum and extreme energy to break matter down to its fundamental units, then guides its thermodynamic reassembly. Steady physical vapor deposition proves that in high-performance engineering, surface aesthetics are engineered atom by atom.